Hello students, welcome to my YouTube channel. In this video lecture, we are going to dive into descent questions from Keith Williams' General Navigation book. In my previous video lecture, I solved the first 10 questions. In this video lecture, I'm going to solve the next 10 questions, questions 11 to question number 20. I'm going to show you how to solve these questions, numericals with formula explanations, so that you not only get to understand how to solve these numericals in your exams, but also get the quick revision of this chapter. Also, I have solved all the 1 in 60 rule questions from Oxford. So do watch those video lectures if you haven't yet. When you watch those video lectures, you will come to know the concept, the formula that I have used, the questions that I have solved from the Oxford textbook. Okay, so there are three types of 1 in 60 rule chapter. 1 in 60 rule 1, in which there is standard formula based questions. Track error angle equals to distance of track divided by distance gone into 60. In the 1 in 60 rule second chapter, that is navigation chapter, you will solve questions based on track error, double track error method, and track error and closing angle. In the third part, that is 1 in 60 rule other applications, you will solve the questions similar to the questions that we are solving in this particular lecture. So watch those video lectures as well. Now, question number 11. If there is a 25 knot increase in headwind, by what amount must the rate of descent be changed, increased or decreased in order to maintain a 3-degree glide slope? Now, if you have watched the previous video lecture, you must be knowing this, that an increase in headwind component must be accompanied by a decrease in rate of descent. Decrease in rate of descent. Why so? Wherever your headwind component increases, the ground speed of your aircraft will further decrease, and that results into an increase in rate of descent. Okay, so I'm writing here increase in headwind component, increase in headwind component decreases ground speed of your aircraft. Correct. This decreases the ground speed of your aircraft and increases your rate of descent. Since you are in the landing phase of your flight, the engine power will be very low, the true airspeed of your aircraft will be very slow, the increase in headwind component further decreases your ground speed. All these combinations make it favorable for a high rate of descent, higher than expected, higher than normal rate of descent. What does that mean? Increase in rate of descent means you will approach the ground surface, you will approach the ground surface at a faster rate. That means you will come down to the ground much quickly. Okay, next. So this is what happens. This is the problem or the challenge that we have just now, that we have seen just now. What is the solution to this part? The solution will be, if increase in headwind component increases your rate of descent, as a pilot, you will stop that from happening. Okay, so you will decrease the excessive rate of descent. You will decrease the excessive rate of descent caused by an increase in headwind component by increasing your engine power. So when you start flying, if you have flown, you must be knowing this. If you haven't flown yet, when you start flying, you will apply this concept when you start doing a solo, when you start learning landing, solo landing, so on and so forth. You will have a practical experience of this. Okay, so decrease the excessive rate of descent by increasing the engine power. So you are deliberately going to increase the power of your aircraft. So when engine power is increased, the true airspeed of your aircraft will increase, and that increase in true airspeed will result or will give rise to an increase in ground speed of your aircraft. So this increase in forward speed of your aircraft will counteract any decrease in the ground speed of your aircraft caused by an increase in headwind component. Okay, so this is what happens. So what is the formula? The formula is the change in rate of descent required is equal to 5 multiplied by change in speed. Okay, so 5 multiplied by change in speed, that is 25 knots. 25 knots increase in headwind will be equal to 25 knots decrease in ground speed. So minus 25. So 5 into 25 is 125 minus 125. That means minus means decrease. So the rate of descent must be decreased by 125 feet per minute. 125 feet per minute. Okay. 5 into 25 is 125. Yes. Next. What will be the rate of descent when flying downslope 5% at a speed of 450 knots? Now we can convert this 5% slope into corresponding angular measurement using this formula tan theta into 100. So 5% equals to tan theta multiplied by 100. So tan theta will be equal to 5 divided by 100, which is 0.05. So theta will be equal to tan inverse 0.05. So shift tan inverse 0.05 is 2.8 or approximately 3 degrees. Now, the rate of descent formula is rate of descent feet per minute equals to glide slope multiplied by your ground speed in terms of feet per minute divided by 60. So glide slope is 3 degree, speed is 450 knots. So 450 multiplied by 101.3 divided by 60. So 3 into 450 into 101.3 is 136755 divided by 60. That is equal to 2279 feet per minute. So rate of descent is equal to 2279 or approximately 2280, 2300, whatever. Next. At 4 o'clock 22 minutes, aircraft is at flight level 370, speed 320 knots, is on a direct track towards VOR. So that means it's flying towards the VOR station, which is 185 miles away from it. Aircraft is required to cross the VOR station or overfly the VOR station at flight level 80, meaning 8,000 feet. For a rate of descent equal to 1,800 feet per minute, ground speed is 232 knots. The latest time at which to commence descent is what? Okay, so at what time will you commence descent to arrive over the VOR station at flight level 80? Excuse me. So let's draw this diagram. This is your VOR station. Okay, here is your aircraft. Now, aircraft is at a height of flight level 370, 37,000 feet. It is supposed to arrive over the VOR at flight level 8,000 feet. Okay, so it is going to fly a straight and level flight for some time. It's going to maintain 37,000 feet for some time, for a few minutes, and then it's going to begin its descent such that it arrives over the VOR at 8,000 feet. Okay, so now current time is 0422. We have to calculate the time it will spend in cruise mode, in cruise phase of flight. How many minutes it's going to spend in the cruise phase, and how many minutes it's going to spend in the cruise phase. The end of the cruise phase will be equal to the beginning of your descent phase. So the point where your cruise ends is the point where your descent of aircraft begins, is where the aircraft descent begins. So we have to calculate the time when the cruise phase, the straight and level flight phase ends and the descent phase starts. Okay, next. Aircraft is how many miles away? 185. So this is 185. Okay, this is 185. Now, the cruise speed of your aircraft is 320 knots. The cruise speed is 320. The descent speed, the ground speed of your aircraft at the time of descent is 230 knots. Descent speed is 232 knots. The rate of descent is 1800 feet per minute. 1800 feet per minute. Okay. Now, first things first. Step 1. We will calculate, we have been given rate of descent. We will calculate the time it takes for this aircraft to descend from 37,000 feet to 8,000 feet. So, time required equals to change in level divided by change in level divided by rate of descent. Okay, so you know the rate of descent formula. Change in vertical distance, change in flight levels divided by the time taken in terms of minutes. So we have cross multiplied. Time equals to change in level. So 37,000 minus 8,000 will be equal to how much? It will be equal to 29,000 feet divided by time taken divided by rate of descent, which is 1,800. So time taken is 29,000 divided by 1,800, that is 16 minutes. 16 minutes. So the time taken to descend from 37,000 to 8,000 is 16 minutes, 16 minutes. Okay. So I'm going to write it here. Time 16 minutes. So now you have distance, you have correction, you know the distance speed of your aircraft, you know the descent time. So using speed distance time formula, you can calculate the distance covered by this aircraft in traveling or in descending from 37,000 feet to 8,000 feet. How much distance it's going to cover? Okay, horizontal distance. So distance will be equal to speed into time. So descent speed 232 knots multiplied by time 16 minutes divided by 60. Convert that into hours. So 232 into 16 divided by 60 is 61.8 or 62 nautical miles. That means out of a total distance of 185 nautical miles, this aircraft is going to cover a distance of 62 nautical miles 62 nautical miles in descending from 37,000 to 8,000. So what is the horizontal distance remaining? 185 minus 62, that is equal to 123. So that means your aircraft will travel in straight and level flight for a distance of 123 nautical miles before beginning its descent phase of flight. Okay, so you know the cruise speed of your aircraft, you know the distance you have to travel straight and level. Now you can calculate time. So time equals to distance divided by speed. So 123 miles divided by 320 knots cruise speed is equal to 23 minutes. That means aircraft must continue its forward journey, its straight and level forward journey for a duration of 23 minutes. After the end of 23 minutes, it can start its descent. So 4 hours 22 minutes plus plus 23 minutes equals to how much? So 4 hours 22 minutes plus 0 hours 23 minutes is 4 hours 45 minutes. That means you will begin your descent at 4 hours 45 minutes. Okay. Next. Aircraft is maintaining a 5.2% gradient, is at 7 nautical mile from the runway. Flat terrain, its height is approximately what? Okay, so now they have interpreted or they have expressed the glide slope in terms of percentage. Let's say this is your runway, this is your glide slope, this is the horizontal distance. Aircraft is here. Okay, an aircraft is 7 miles from the runway. Next, we have to calculate the height of aircraft. So we can calculate that when we using trigonometry ratio or 1 in 60 rule. For that we must know the glide slope in terms of angular measurement. So let's convert the glide slope in terms of percentage given to us in terms of angular measurement. So slope equals to tan theta into 100. So 5.2 percentage equals to tan theta into 100. So tan theta will be equal to 5.2 divided by 100, that is 0.052. So theta glide angle equals to tan inverse 0.052, which is equal to shift tan inverse 0.052, 2.9 or approximately 3 degrees. So this is equal to 3 degrees. Now let's use the 1 in 60 rule formula. Angle equals to distance of track divided by distance gone into 60. So 3 degree distance of track. This distance of track is the height of aircraft. We have to find that out. Distance traveled 7 miles into 60. So x equals to 3 into 7 divided by 60. Okay, convert this 3 into 7 nautical miles in terms of feet. 1 nautical miles equals to 6080 feet. So 6080 divided by 60. 3 into 7, 6080 divided by 60 is 2128 feet. That means aircraft is approximately 2130 feet above the ground surface. Now let's use what? Let's use trigonometry formula tan theta. So tan theta equals to opposite upon adjacent. So tan of 3 degree. Opposite side is unknown to us, the height of aircraft. Adjacent side is 7 nautical miles. So height of aircraft equals to 7 nautical miles multiplied by 6080 feet into tan of 3. So tan 3 into 7 into 6080 is 2230. Okay, 2230 feet. So okay, so using tan theta formula we get the value equal to 2230 feet. Using 1 in 60 rule we are getting a value of 2130 feet. So use that option or select that option which has any value which is closest to any of these. Next, if there is a 10 knot decrease in headwind, by what amount must the rate of descent be changed to maintain a 3-degree glide slope? Now, so far we have been tackling questions which involved increase in headwind component. Now in this particular question there is a decrease in headwind component which can also be expressed as increase in tailwind component. A decrease in headwind component is nothing but increase in tailwind component. Now we all know that if there is an increase in headwind component, what problem happens? What kind of problem happens? The rate of descent increases more than required, more than required. Okay, if there is an so what will happen if there is a tailwind component or increase in tailwind component or a decrease in headwind component, same things or similar things. So what happens when this happens? Rate of descent will decrease. The rate of descent of your aircraft will decrease. So your aircraft will tend to remain in the atmosphere, will tend to remain suspended in the atmosphere. It will refuse to come down. Okay, in a headwind component, in a headwind situation, it comes down excessively. In tailwind scenario, it refuses to come down. It remains suspended or lifted in the air. Okay, so rate of descent decreases more than required. Okay, so reverse happens. Now the solution. What is the solution? When rate of descent increases more than required, when it is excessive, as a pilot, you will decrease that excessive rate of descent. You will curtail it. You will avoid that, or you will prevent that from happening. So decrease the excessive rate of descent. And if a tailwind component decreases your rate of descent, the solution will be the exact opposite. You will decrease engine power, and you will help your aircraft or aid your aircraft in achieving a proper stable rate of descent. Okay, so you should do whatever is required to increase the rate of descent of your aircraft. Increase the rate of descent of your aircraft to a normal value. Over here, you're going to decrease the rate of descent of the aircraft to a normal expected value. Okay, so formula remains the same. The change in rate of descent required is equal to 5 multiplied by change in ground speed. So 5 multiplied by, now 10 knot decrease in headwind. Whenever there is an increase in headwind component, your ground speed decreases. So when there is a decrease in headwind component, meaning when the headwind component decreases in magnitude, the ground speed of your aircraft, the forward speed of your aircraft with respect to the ground will increase by the same amount. So a decrease in headwind or increase in tailwind by 10 knots will increase your ground speed by 10 knots. Okay, so 5 into plus 10. So that will be the change in your ground speed plus 10. So 5 tens are 50. So 50 feet per minute. So the rate of descent will be 50 feet per minute. That means you will rate of descent of your aircraft must be increased. Plus means increased. Must be increased by 50 feet per minute. Next. What will be the rate of descent when flying down 8% slope at a speed of 400 knots? So again, slope equals to tan theta multiplied by 100. So 8% equals to tan theta into 100. So tan theta equals to 8 divided by 100, that is 0.08. So theta equals to tan inverse 0.08. Is equal to 4.5 degree. Okay, next. Rate of descent equals to glide slope into speed divided by 60. So glide slope 4.5 degree. The ground speed of your aircraft 400 knots multiplied by 101.3 feet per minute divided by 60. So 4.5 into 400 into 101.3 divided by 60 is 3039. Okay, or approximately 3040 feet per minute. So select that option which has a value close to this number, closest to this. Aircraft is flight level 350, arrives at VOR 8000 feet, flight level 80. What is the rate of distance required when you are 85 miles away at a speed of 340 knots? Okay, let's plot this. So this is your VOR station. Here is your aircraft. 55,000, 8,000. Okay. You are 85 miles away. Speed. The ground speed of your aircraft is 340. Distance is 85 miles. Now when you know the speed and distance, you can calculate time by using speed distance time formula. So time equals to distance by speed 85 divided by 340. So that is equal to 15 minutes. Okay, so you have a time limit or a time period of 15 minutes to descend from 35,000 feet to 8,000 feet. Rate of descent formula is change in height divided by the time. So what is the change in height that you are going to effect when you descend from 35,000 feet to 8,000 feet? It will be equal to 35,000 minus 8,000, that is 27,000, right? So change in height 35,000 minus 8,000, 27,000 divided by time 15 minutes. So 27,000 divided by 15 minutes is equal to 1,800 feet per minute. Okay, so this is your answer. Next, if there is a 15 knot decrease in headwind, again, a decrease in headwind meaning increase in tailwind component. By what amount must the rate of descent be changed in order to maintain a 3-degree glide slope? So change in rate of descent is equal to 5 into change in speed. So 5 into change in ground speed. Now a decrease in headwind component, okay, will increase your ground speed by that much amount. So if headwind component decreases by 15 knots, it will increase your ground speed by another 15 knots, right? So 5 into plus 15, correct? 5 into plus 15. So 5 into 15 is 75. So answer is 75 feet per minute. Okay. So solution, the rate of descent must be increased. The positive sign signifies an increase in a factor. So rate of descent must be increased by 75 feet per minute. Okay. Whenever there is a 15 knot decrease in headwind. Next. Aircraft is at flight level 290 and 50 miles from a VOR. It has to cross that VOR at 8,000 feet. Speed 271. What is the rate of descent? So similar question. So this is your VOR station. Okay. Here is your aircraft. So 29,000 feet से लेके 8,000 feet. 50 miles. Horizontal distance is 50 miles. Speed is 271. So Knowing speed and distance, we can calculate the time required for descent. Time equals to distance by speed. So 50 miles divided by 271 is equal to 11 minutes. So rate of descent equals to change in height divided by time. So change in height that will be made from descending at a height of from descending from a height of 29,000 feet to 8,000 feet will be 29,000 minus 8,000, 21,000 divided by time 11 minutes. So 21 divided by 11 is 1909 or approximately 1910 feet per minute. So the rate of descent will be equal to 1910 feet per minute. Equivalent of 70 meter per second in terms of knots. So we all know that 1 knot equals to 0.515 meter per second. So 70 meter per second will be equal to how many knots? So 70 divided by 0.515, that is equal to 136 knots. Okay, 136 knots. Convert this into feet per minute. So 136 into 101.3, that is 13776 feet per minute. 13,776 feet per minute. So this concludes the lecture. I hope you have understood all the 10 questions that I have answered in this video lecture. If you have liked this video lecture, do hit the like button, subscribe if you haven't yet, and share this video with your friends. Thank you for your time. Best of luck.